So let's take a look at what we have. So it says this figure right here, 5.3, shows a 5 kilogram block A, which hangs from a string which passes over a frictionless pulley and is joined at the other end to a 12 kilogram block B, which lies on a frictionless table, right?
Okay. Yeah.
Find the acceleration of the two blocks. Now, both blocks will have the same acceleration. So the acceleration of the system is what we need to find. Also find the tension in the string, right? So the tension in the string here. What would the tension be if block B were fixed in place? Okay, so technically a three-part question, because we also have to say what the tension would be if B was fixed in place. All right. So here's my diagram, right?
Okay.
So the first thing is we need to determine the net force on both blocks A and B. All right?
Okay.
We don't have to draw a free body diagram here. It's pretty much been labeled all the forces that are acting on A. You have the tension force upwards and the gravity force downwards. Do you see? And
Okay.
on
Yeah.
force B as well. So we don't have to draw a free body diagram. That's been taken care of. Now, where should we start? Well, so what we need to do is determine the net force on A and the net force on B. Well, that's where we're going to start. Yeah. But before we do, let's assign which direction will be positive. The direction that you should assume to be positive should be in the direction of the assumed acceleration. And what do I mean
Okay.
by assumed acceleration? Well, obviously this block is hanging, so you would assume that this block would pull on this block, and so the acceleration would be to the left here, right?
Okay. Yeah.
So therefore, we will say that is the positive direction for acceleration. Understand?
Okay.
Does that make sense?
Yeah. Yeah. Makes
Okay.
sense.
So that's what we're going to use as the positive direction to the left, because acceleration we assume would be to the left. Now, what about upward or downward? Well, the thing is that since this is the block pulling on the other block, then we see that acceleration is not only to the left, but it would be downwards, right?
Yeah.
So downwards would also be considered a positive direction. Do you understand?
Okay. Yeah. Understand.
So left and downward is what we're going to take as the positive directions. So let's write down what the net force on A is. Now the net force on A, if we look at A, we have the force of gravity downwards. And then we have the tension force that is upwards. So minus, because we said downwards is positive. Understand?
Okay. Okay.
Right? So
Yeah.
that's what's going to
Oh.
happen there. Now, the thing is, the tension for the block A is upwards. In which direction would the tension for block B be? Well, to the left, right?
Right.
In
Yeah.
fact, actually, that's given to us in the diagram. You can see that in the diagram. It's to the left, the tension of force B. Okay? So the idea is, if you want to remember it as a pattern, the arrows, this arrow should meet that arrow. Okay, if you want to remember it that way. So that's the equation for the net force on A. Now we know the net force on A is the mass of A times the acceleration of the system, which is what we're trying to find, right?
Okay.
And On the right side, it's 4 o'clock, but that's fine. I'll finish this because I came late as well. So force of gravity is mass times acceleration due to gravity minus the tension in the string. Well, that's what we need to also find. So that's the equation for the net force on A. All right.
Okay.
Now let's take a look at the net force on B. Now the block is only moving to the left. If this block A is pulling down, then block B would be moving to the left. So therefore, for B, the force of gravity and the normal force won't mean anything because the net force in the y direction will be 0. So therefore, the normal force would equal to the force of gravity on block B. But we don't need to know that in order to solve this. Do you see? Because we're only
Okay.
interested in the block moving that way. So the acceleration would be that way, not up or down. So the net force on B would, of course, be simply given by that tension. Do you see?
Okay.
And that's all we would have. Understand? Do you see any other
Okay.
forces that would be acting on B? No, that's it, right?
Yeah.
And we know the net force on B, according to Newton's second law, would be mass of B times the acceleration of the system. And that is what T is equal to. Do you see?
All right.
And there
Okay.
is no friction here. If there was friction, then it would be that way to the right, and we would say tension minus friction. Do you see?
Okay. Yeah.
But there is no friction, so that's all. Mass of B times acceleration equals to the tension. And now what we can do first is do a little substitution. So we can substitute this T equals MBA into this T. All right, so we're going to basically sub in this equation into that T. So now here we have mass of A times acceleration equals to the mass. And by the way, this is also mass of A because gravity is only acting on A. Right, well, it's A's gravity because that we're concerned with. So mass of A, gravity is pulling it down. So mass of A times acceleration equals to, now actually, yeah, let's plug it in. So mass of A times gravity minus the tension, which is equal to mass of B times acceleration. Understand?
Okay.
And now here we can solve for A. So we have mass of A times acceleration plus mass of B times acceleration equals to mass of A times gravity. We can
Oh.
factor out acceleration and we're left with mass of A plus mass of B equals to mass of A times gravity. Do you see where I'm going with this?
Okay. Yeah. I see. I
So
see. I also
now you
see where you
divide
mean.
both, right, now you divide both sides by that total mass. So acceleration equals to the mass of A times gravity over the mass of A plus mass of B. So
Okay.
now we can find the acceleration. Mass of A, you can see from the diagram, is 5 kilograms times gravity 9.8 meters per second squared, or acceleration due to gravity. Mass of A, again, 5 kilograms, plus mass of B, 12 kilograms. So 5 times 9.8 in the numerator is 49, and 5 plus 12, so that's 49 kilograms times meters per second squared. And in the denominator, we have 5 kilograms plus 12 kilograms, 17 kilograms. Of course, the kilograms divide out, leaving you with meters per second squared. So quickly, if you may take your calculator, and could you please tell me what 49 divided by 17 is?
2.9.
Which is what I said the answer should be, right?
Yeah. Okay. I see where I made my mistake.
Do you see now? And now that
Yeah.
we have our acceleration, we can substitute that acceleration value right here, up here, and find tension. Do you see?
Okay, yeah.
Up here. So what is tension equal to? Well, now we can see that tension is equal to the mass of B, which is 12 kilograms, multiplied by the acceleration, which was 2.9 meters per second squared. So what is 12 times 2.9?
12 times 2.9. 35.
And that's how we get tension to be 35 newtons. Do you see?
Okay.
Then you write a final statement, therefore statement, and that's that. So do
All right.
you understand where you went wrong?
Yeah, I put it as force tension minus force gravity. It should be force gravity minus force tension. Okay.
Perfect. So see, directions are important. So first determine which direction is positive and which direction is negative. So assume the positive direction in the assumption of the acceleration. So if you assume the acceleration is downwards because common sense tells you, oh, well, this A is pulling on B, so the acceleration should be downwards and B should be moving to the left. So therefore downward and left would be positive directions. Do you see?
Okay.
All right, having said that, I will see you